Last week we learned about a single cycle implementation where the instruction passed all the way through a data cycle in one cycle. So you input the instruction, and in one cycle through the data path, it interpreted and carried out the instruction. This week we look at multi-cycle. So the instructions are going to be broken up into a number of micro instructions, and each micro instruction will go through the data path. So we're going to have an instruction, our 32 bits instruction is going to get turned into a number of micro instructions, and each micro instruction will go through the data path, have its own control signals, and then when it's done, do another micro instruction. So it's like each instruction is a little program. And so each instruction could take 3 cycles, 4 cycles, 5 cycles, depending on how many micro instructions it takes. So the longest step is going to determine the clock periods. Whichever step takes the longest is going to be the cycle time. Generally, the longest longest step is going to be accessing memory. And we're also going to have different control signals and a change in state with each cycle. And we're going to talk about a finite state machine and how that is going to model our behavior. So a finite state machine contains inputs, so the inputs are going to be the instruction, outputs, which is going to be the result of the instruction or carrying out the instruction, and a map, a way of going through different states to carry out the instruction, where each state is going to be a cycle. So here's a picture. We're going to have inputs. That's our instruction. And a clock telling it, where, the clock is going to control, when a new cycle happens, where we are now, where we have to go next is going to be controlled by where we are now and the instruction. What kind of instruction are we? Will determine where we go next. And then the output, which would be the result of adding two numbers together or doing a shift operation, is going to be also the result determined from where we are now and the instruction. So just like before, the instruction told us, what registers are we reading from, what operation are we doing, this is going to be doing that operation. It's just that our whole instruction carrying out is split into multiple steps. So hopefully this will get a little clearer. It's this particular lecture is kind of hard. It takes a while to put the whole thing together, like what I'm talking about. So hopefully by the end you'll figure this out. Okay, so let's talk about the control unit. Hopefully this will get clearer as this goes along. So just like in this single cycle, we had a control unit. In this one we do 2, and the control unit is going to be the values of the control unit signals are going to be controlled by the opcode. So the opcode says, what kind of instruction is this? So that's how you're going to get your control unit values. And the outputs are going to be the control signals again. So it's telling the ALU where to get its input from. It's telling the program counter where to get the next instruction from. and so on. And then we also have to calculate the next state. So again, we're splitting our instruction up into a number of cycles, and each is a state on a finite state machine. And so once we've done this micro instruction, what do we have to do next? Hopefully this will start getting clearer. So again, a picture. This is our logic for our control unit. We're going to input the opcode. We're going to input what state we're in now, and we're going to output control signals and where to go next. And here's a picture of our data path. So this will come in handy later, but this is our first look at it. So again, keep this in mind to come back to, because again, I know I've said this a number of times, it takes a little while to put all this together. But so this is your first look at this data path, and just keep in mind that in each cycle it goes through this entire data path. So each cycle it goes through this data path. So the first part of the cycle could be just incrementing the program counter. The next cycle could be calculating the memory address for a load word. The next cycle after that is going to memory. So where before it did everything it needed to do to interpret the instruction in one, this is going to split it into pieces. And so here are our control signals. They're slightly different than for the single cycle, and they're going to change with every cycle. Here's our control unit. You can see there's lots of different choices here. There's two choices for where the top input to the ALU. It could be either the program counter, so we could be just adding 4 to the program counter, in which case the top input would be 0, which would be the program counter, and the bottom input would be 4. We could be reading registers for A. B could be reading registers. It could be the sign extended immediate value. It could be the shifted left value if we're doing a jump. So these are all the choices that could go to the bottom input of the ALU, and so on. So it's a little more complicated. There's more options here. And again, keep in mind that it's going to go through this data path multiple times for each instruction. So we'll come back to this. And this is for your reference. These are all the different values you can have in the control unit. So the ALU control field is, what is the ALU going to do? Is it going to add, subtract, or is it going to depend on the function code? So if it's an R type, it's going to read that most significant 5-bit function code, and so that's going to be the input, and it's going to use that function code to determine what to do with the ALU, or it can add or it can subtract. This source 1 is the upper source of the ALU, source 2 is the lower source of the ALU, so there's a number of different things you can do since this is multi-cycle. If you recall, in the single cycle there were a number of adders in there, like there was 3 or 4 adders. Here there's only one ALU, so that has to serve all the purposes that you would need to use an adder. So that's why there's so many choices for this bottom input to the ALU. Register control, are we reading 2 registers? Are we writing to the writing back? Like if I was an R type, are we writing back, or are we writing from memory? Are we doing something with the memory? Reading a program counter. So that's just, are we reading an instruction? So that would be the fetch. So there's this control signal called I or D, so that's instruction or data. Are we reading data from memory? Are we writing data to memory? Are we going to write a new value of a program counter? So we can either write the output of the ALU, which would be adding 4 to the program counter. Is this a branch or is it a jump? And this is, where do we go next? And we'll go through that. Do we just go to the next one? State. Are we done and we're going to go back to state 0? Or we'll see in a minute what these dispatches are where there's a choice. So again, you haven't even seen the finite state machine, but it's kind of like difficult to figure out what order to put these slides in to get it all together. But you can come back to this if you're, want to put it all together. Again, we've seen this. So this is our actual control unit. So our input is going to be what state we're in and the opcode, and these are our outputs. So I kind of just talked about these outputs. Are we writing a new value of program counter? Is there a conditional write? Are we doing something with instruction or data memory? Are we reading from memory? Are we writing to memory? And so on. And finally, here's our state diagram. So every time we read in, so this is just, again, a small set of instructions, just like with our single cycle data path. We're only having a small set of the instructions just to keep it reasonably simple. So again, we have R type, load word, store word, branch on equal, and jump. So this is the multi-cycle state diagram for just these. And so each time we read an instruction, we're going to turn that into a number of micro instructions, and each micro instruction is going to be represented as one of these states. And so each state here is a micro instruction with its own set of control signals, and it's going to go through the data path in one cycle. So we fetch an instruction, and here's the control signals associated with fetching an instruction. Then we're going to decode the instruction and possibly determine what registers are being used. And then as we decode, we're going to determine from that opcode whether it's a load word or store word, an R type, a branch on equal, or a jump. Okay, so this is going to be determined during this instruction decode. So if it's a load word, it's going to go to this state with these control signals. And so what these control signals are going to tell it to do is calculate a memory address where we're going to load data from or store data to. If the opcode says it's a load word, we're going to read memory. And then we're going to write back memory. And then we're going to be done and go back to state 0 and get the next instruction. If it's a store word, the opcode tells us it's a store word. We're going to access memory. Sorry about that. We're going to write to memory and go back. So this is just saying, if I'm going to do that instruction, I have to go through all these steps, and each of these steps are going to be one cycle. If it's an R type, I'm going to come to state 6, and the ALU is going to do its execution. So that's why we have this ALU op equals 10. That's the one where you use the function code to determine. I'm going to write back to my register and finish. So if I'm a load word instruction, I'm going to go through states 0, 1, 2, 3, 4. That's a load word. So a load word is going to take 5 cycles and do these 5 steps. Each of these steps is going to be a run through the data path. a store word is going to go through states 0, 1, 2, and 5. Each state being its own, having its own set of control signals and going through the data path. R type is going to do 0, 1, 6, 7. So that's 4 cycles. Branch on equal is going to be 0, 1, 8. And jump is going to be 0, 1, 9. So they're each 3 cycles. And 3 micro instructions. So hopefully now all that stuff from earlier is a little more clear. So the control signals we talked about in the last slide are here, the values for those control signals. Here, each state has an input, and that would be the opcode or where we are now. Okay? And again, the output control signals are determined by what state you're in. The PC write control signal is always on when you're in state 0 or 9. So this is, I'm writing a new value of the program counter, and that's going to be true if I'm in state 0 because I'm just adding 4 to the program counter, or state 9 where I'm doing a jump. PC write conditional, our conditional is branch on equal, so if I'm in state 8, I'm going to branch on equal, and this is true. So these are saying that when each control signal is set, can be determined just by what state you're in. So here's our state. State 0. We have on the PC write control signal, mem to read, and IR write, and ALU source B0. So you can look at that finite state diagram and look at the control signals that are listed in there, and that's how this is determined. Okay, so the control signals are a 16 bits. And so really, we're going to talk about micro instructions that can be either 20 bits or 18 bits. And 16 bits of those micro instructions are these control signals. Okay, so this is the same thing, but kind of put in a different, set in a different way, where this is along the top in the last slide, and this was vertical. We've just kind of flipped it. So if we're in state 0, this is the 16 bits of our control signal. And so if our micro instruction is 20 bits, which would be the upper 16 bits are these control signals, and the lower 4 bits are the next state, which we haven't really talked about yet. This would be how you would determine them. So again, we take a 32-bit input instruction. We're going to turn it into a number of micro instructions. The upper 16 bits of those micro instructions are those control signals we talked about in the last slide. The lower 4 bits are the next state. Okay, so each micro instruction is going to be 20 bits in this case, and it's going to tell it what to do using those control signals and where to go next with the next state. So if I'm in state 0, no matter what kind of instruction, so again we talked about how we have a small set of instructions, R format, jump, branch on equal, load, and store. But if I'm in state 0, 1 is always going to be next. If I'm in state 1, we saw from our finite state machine diagram that there are several places we can go next. We can go to state 6 if it's an R format, state 5 if, or 9 if it's a jump, 8 if it's a branch unequal, 2 if it's a load word or store word. So this is the next state. If I'm in state 2, I have to be either a load word or store word, and I can either go to 3 or 5. If I'm in state 3, I must be a load word. So I'd have to go to 4. So it really can only be a load word. So there should be X's. And so on. So if I'm in state 4, I have to go back to 0. And again, I would only be in a load word or store word. I would only be in a load word. So there should be more X's in here. But anyway, this shows you where you go next from each state. And here's another way of looking at the next state. So if I'm in states 4, 5, 7, 8, or 9, the next state is always 0. If I'm in state 0, the next state is always 1. And so on. If I'm in state 1, I have to be in a load word, store word, and the next state would be 2. So phew, getting complicated. We're putting it all together. Again, for our control unit, our input is the opcode and where we are now. So that's a 10-bit input for each instruction. Output is going to be the 16 control bits and where to go next. And that's the micro instruction. Okay? So doing one instruction is a sequence of states, and each state has an input, and the 20-bit output data micro instruction, and it goes through the data path. And each state is one step and takes one clock cycle. So now we're going to talk briefly about how we make a control unit. So that control unit, that's just the control unit, takes the 10-bit input and turns it into a 20-bit output. So a 10-bit input is going to have a total of 2 to the 10th or 1024 possible inputs. And then 20 bits output. So if we had just a table of just inputs where we had every possible combination of 10 bits times a 20-bit output, that would be how big our table would have to be. Which in the earlier days of computing cost a lot. But we don't really have 1024 possible inputs or 10, it's really a lot smaller than that. Sets of where we are now state and opcodes. There's not that many possibilities really. So we're going to show how we can store it in a programmable logic array that's a lot smaller than 1024 times 20. So we learned about min terms. We learned about sum of min terms or products. So a min term is an AND of one or more inputs, and it's going to correspond to a single entry. And so a possibility would be if we're in state 0, then the bits, the 4 bits of the state would be 0 and 0 and 0 and 0 and so on. You'll see what this means, but we're going to have a bunch of possible states. That would be those 10 bits. And we're going to see that rather than 1024 times 20, there's really only 17 possibilities. And so we make a PLA that's a lot smaller. than 10, 24 times 20. Like, instead of 10, 24 possibilities, it's really 17. And so then we have 17 possible outputs, and so it's a lot smaller. So let's see how we implement. So here's our 10-bit input. And like we said, there's 17 possible sets of products. So there's 17 combinations of inputs that we care about. And these are our outputs. Each control signal and the 4-bit next state is a line here. So this would be one control signal, maybe PC write. So this would be what sets of product terms have to be on for PC write to have a value of 1. Okay, and so there's a line for each of the control signals we talked about and the next state. And here is our PLA implementation. So just like I said, PC write is this top one, and here's PC write is going to be true. There's 2 minterms, so each of these is a minterm. So PC write is true if we're in state 0, so that would be not, so these are the 4 bits of the current state. So if each of the 4 bits of the current state are 0, this in front of this NOT gate, if S3 is 0 and S2 is 0 and S1 is 0 and S0 is 0, if this is a minterm, not S3, not S2, not S1, not S0, all ANDed together, if that's true, then PC write is true. Or the other was if we're in state, I think it's 9, right? So that is if S0 is 1, S1 is 0, S2 is 0, and S3 is 1. So if that's true, then PC write is true. So each of these vertical is an and then this would be or. So if this line is all true or this line is all true, then PC write is true. Okay, so we can see all the states that would cause the different control signals to be true. And here are the bunch of, so sometimes the opcode values are true. Like I just said, each vertical line in the PLA is a minterm, so it's a set of ands. We saw the leftmost 10 depend only on the state, and then the remaining 7 depend on the state and the opcode. The top half is the AND plane. The bottom half is the OR plane. If we want to make it even smaller, we could just have that one, the 10 that come from just 4 inputs and the 7 that come from 10. If we could make two littler PLAs. But here's this again. So we can see these here. The values here depend only on the current state. Here's the one if we're an R type, or where we need to make a choice based on what kind of instruction is going to be these where it depends on the opcode. So this was a very simple finite state machine with only 10 states. Obviously, we're only doing a couple different kinds of instructions. A more realistic system would have a lot more micro instructions and a lot more states. Again, recall that each state in our finite state machine is represented by a micro instruction. And then most of the time we're going +1 or we're going back to 0. There's a couple different choices. Times when we could go to different states based on the opcode. So we always go from 0 to 1, we always go from 3 to 4, 6 to 7. We always go from any of these to 0, but here's a choice and there's a choice. Here's a picture again. So here's a choice and there's a choice. So really the programming we have to do is just, the only time we need the opcode is when we're here or here, in 1 or 2. And we can just use small lookup tables if we're having to choose. So we have a new control bit here. We could use some logic. So this adder control is going to say, all right, what do I do next? Do I just add 1? Do I go to 0? Or do I have to choose the next state based on some logic? So there's 4 choices. I could have that choice of 4 state, I could have that choice of 2 state, I could go to the next state, or I could go to 0. So that's why this adder control is 2 bits. And again, here's our 4 choices. Go to 0, make a choice using ROM1, make a choice using ROM2, or go to the incremented state. As we saw, ROM1 could be the one where we chose whether it's a load or store, an R type, a jump or branch, and ROM2 could be, is it a load or a store? So again, yeah, ROM1, what's the opcode? If it's an R format, I go to 6 next. If it's a jump, I go to 9 next, and so on. ROM2, here's the opcode. If it's a load word, I go to 3 next, and so on. And here's just the whole thing put together again. So if I'm in state 0, I always use the incremented state, so the value would be 3. If I'm in state 1, I have to choose whether, based on what kind of instruction I am, so use ROM1. If I'm in state 4, I always go to 0 next, so I the control is 0. And here, instead of, so in the last one, we showed earlier a 20-bit control word where we just used 4 bits to describe the next state. Here it's just using the 2 bits, using this adder control. So it turns it from an 18-bit 20-bit micro instruction to a 18-bit. It's a little smaller. So if we're in state 0, this is our micro instruction. This is how we tell the data path what to do. So these are our 18-bit instructions. If I'm in state 1, this is my micro instruction. So this whole long-winded thing was to tell you how you get the set of micro instructions. So, going through all this, each micro instruction is 1 step, takes 1 clock cycle, goes through the whole data path. A machine instruction, your 32-bit instruction that we studied the last couple weeks, is going to make a micro program. So just like a load word is going to turn out to be 5 18-bit instructions, from state 0, 1, 2, 3, 4. So the load word is going to be that sequence of microinstructions that we might put on a chip, and we're going to have to retrieve and execute microprograms. But it does provide flexibility. If we need to change the microcode, we can do that because it's not hardwired. It's using those programmable logic arrays, and it can be changed. Whereas RISC systems really don't use this kind of thing. They use hardwired logic that's faster. So this is really a CISC kind of thing.